And looks like we're recording. All right. Hi, Kim. Coming back for our second lesson here. I'm doing 3.9 ion formation. You'll notice that we're skipping 3.8 quantum numbers. I was going to skip that originally anyway. It's not really important for us right now, but especially now that we are kind of going to be short on time for this semester, I don't think it's something we need to cover, but ion formation is very, very important when we're talking about reactions. So we need to understand how to predict charges on a simple ion. So we're going to take a look at this today, and we're going to understand the difference between the two kinds of ions. We have cations and we have anions, and we're going to understand how to acquire charge and switch from atoms to ions. We said earlier in earlier standards at the beginning of the year, those two are not the same. Atoms and ions are very different, and we're going to see that again as we go through our lesson here. First off, I want to come back to talking about ionization energy here, IE, and that brings about this concept of stability. And I really want to kind of get away from talking about stability. A lot of teachers will introduce the noble gases by saying these are very stable. And that's true. They are very stable, but it is due to the ionization energy. So I talked last week about the ionization energy really quickly. But again, in case you missed the last video, or it's just not quite in your memory, ionization energy is the energy needed to ionize an atom. So we're talking about losing an electron, how much energy to essentially eject an electron off of the atom, out of those valence electrons. This group, because this shell is complete, energetically speaking, it is favorable to have a complete shell. So it takes a lot of energy to disrupt that complete shell. So the ionization energy of noble gases here, this group, 18, is very high. So it makes them stable because they are not charged, as the rest of our elements will be charged normally. They'll turn into ions. When we talk about stability then, we talk about electron configurations that we are trying to get to. We're talking about noble gases. Okay? Everything's going to come back to the noble gases here on the right-hand side. And if my mouse isn't clear here, I think I can highlight this. Oh, yeah, sorry. I don't have a pen with me, so I'm doing this with my mouse. This group, number 18, far right-hand side here. Okay. No. We're going to keep going. And I hope my computer is okay with the drawing thing. I might have to give it a sec. Keep going. All right. Here we go. Essentially what we're doing when we're looking at electron configurations is we are trying to model them after the noble gas configuration. Like I just said, noble gases have extremely high ionization energies. They're the baseline electron configurations that we are going to refer to from now on. They're the complete electron shells. Let's take a look at fluorine here then. Right here. If I need to mark it, it is right there. Okay, element number 9 on our periodic table. I want you to take a quick second here. Think about how many valence electrons it has. And like I said in the previous video, this is where you would pause the video so you get that answer in. Okay. Valence electrons, as we said last week, are the electrons in the highest energy shell. For fluorine, we have 1s2, 2s2, 2p, 1, 2, 3, 4, 5. Our highest energy level is energy level 2, and we have 1, 2, 3, 4, 5, 6, 7 electrons. So in total, yikes, can I do this with my hand? That's a little bit better. Okay, we have 7 electrons, 7 valence electrons in fluorine. I'm going to get rid of this because I think it makes it a little difficult to see. When I say how many does it need, I'm talking about how many more electrons or how many fewer electrons do we need to reach the nearest noble gas. Fluorine, it's pretty obvious that the nearest noble gas is neon. It's just one away here. So how many electrons do we need in order to get to neon? If you said just one more electron, that's what we're looking for, right? If you think about our electron configurations here, and I'm going to come over to my other drawing tool. It looks like this is already set up. So fluorine, we said is 1, come on, S2, 2s2, 2p5. And neon, the noble gas that we're trying to get to, is 1s2, 2s2, 2p6. The difference then, whoa, don't do whatever that just was. The difference then is in our 2p subshell. Neon has 1 additional electron compared to fluorine. That's what we're comparing, is the electron configuration. So how many electrons does it need? 1 more electron. Now how do we get those electrons? This is kind of a question that I don't really expect you to know right now, but the answer is we'd get them through chemical reactions. Every reaction that we see, chemically speaking, is just atoms and elements trying to get a balance of electrons. Really, all reactions stem from are these imbalance of electrons, these ions trying to get themselves stabilized. Everything comes back to balanced energy. Okay, I am going to erase this because I don't think it's going to let me skip slides until I get out of this drawing mode. So save changes, no. And then it's going to take a second here. Okay, next slide. Are we ready? Ionization. Here we go. How do we get those electrons? We ionize the atom. So ionization, and this is something you should probably have in your notes and know from now on, is converting an atom to an ion by either removing or adding an electron. And remember our big point here, ions and atoms are not the same thing. Atoms are always, always, always going to be neutral. And ions are going to have a charge because we are adding or removing electrons. Now we said there were 7 valence electrons in fluorine. And if we want to prove that, we just come back here to our drawing and we say, oh look, we have 2s2, 2p5, 2 plus 5, that's 7 valence electrons. and we need one more. Remember, we're trying to get to the nearest noble gas, which is neon. So 2 plus 6 is 8. The difference between 7 and 8 is 1 more electron. If we add that additional electron, what's the charge on fluorine as an ion now? Okay. The charge is now negative. Okay. We would write this down as fluorine being F, and then in a superscript here, negative. If you're thinking about, or maybe confused about adding an electron and it becoming negative, remember that we're talking about charges. Electrons are negative charges. So when we add electrons, we are adding negative charges. If we added 2 electrons, then we would have F2 minus, because we added 2 negative charges. We added 2 electrons. I find that this is a place where students get a little bit confused, because we talk about adding negatives, and it's kind of difficult for some people's brains to wrap around a little bit. The other direction for that, right, is if we remove electrons, then it's positive. So subtracting negatives makes it positive. So if we took an electron away from fluorine, all of a sudden this is, this is fluorine positive, because we removed an electron. We took away a negative charge, which means there's one more proton than there are electrons. So there's one more positive charge than there are negative charges. Just something to keep thinking about. And if you have questions, I'm sure I can explain it to you personally a bit better than I'm doing in this video. But there's just a lot of content that I'm trying to get through for this video, so I don't want to waste too much time discussing this. Okay, we're going to keep moving on here. Oh, this is frozen in place until I exit. No. How are we doing for time? 13 minutes, okay. I'll try to be a little bit quicker. I don't want this to drag on for you too long. We just talked about ionizing fluorine. Okay. I want to skip electron affinity for now. Essentially, no, I do want to skip it. I do want to skip it for now. We're not going to talk about electron affinity right now. We'll bring that back for Unit 4. So, if you're looking at the periodic table, we're just essentially marking down things until they reach the noble gas. So fluorine is one position away from the noble gas. So we add an electron, right? 9 over to 10. The charge is F negative, 1 electron over. So we have 2 types of ions, an anion, which is negative charge, or a cation, which is positive charge. Fluorine then, our F minus, would be an anion, has a negative charge. Cation, like sodium here, Na plus, would be a positive charge. If you gain electrons, you're an anion. If you lose electrons, it's a cation. Now, this can go both ways, right? Because we have positive and negative charges. The charge on sodium, then, is something we should look at. Now, sodium, right? You might look at the periodic table and you're like, wait, Mr. Brester, if I look at sodium, I have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. That's the nearest noble gas, right? Why isn't sodium 7 minus? Now, like I said, this goes both ways. So what you actually need to look at is which noble gas is closer, because we can go backwards in the periodic table too, right? Sodium 11 minus 1 is neon 10. So if we subtract an electron from the configuration of sodium, it now has neon's electron configuration. If we took an electron away, what is the charge on sodium? Yikes, this is bad. Hang on. I'm going to do this with my finger, I think, because drawing this is not working out too well. If you said Na+, you're right. We took away an electron. We went over here from 11 down to 10. Now remember, this is still sodium. It's just with neon's electron configuration. So what we're doing here is not changing this to neon. It still has 11 protons. It's still sodium. It's just a sodium ion with 10 electrons. What would the charge be on oxygen if it was to ionize? Well, let's come over here to oxygen. And we take a look at oxygen. And we say oxygen could gain 1, 2 electrons and be neon's electron configuration. Or it could lose 1, 2, 3, 4, 5, 6 electrons and be at helium's electron configuration. Which one do you think is more energy efficient, to gain 2 electrons or to lose 6? That's right. We're going to gain 2 electrons because losing 6 sounds like way more work to me than gaining 2. Okay, and it's again comes down to energy efficiency. The universe tends towards minimum energy, so gaining 2 electrons is much more efficient than losing 6. Our charge on oxygen then is going to be what? Gaining 2 electrons should be O2 minus. We're gaining 2 negative charges. All right. No change here. We've got one last thing. Actually, 2. There's some practice here, and then there's one thing that I don't mention on these slides that I do in the homework that I want you to do. So try this out for me. Calcium, bromine, lithium, nitrogen, potassium, carbon. What's the charges on them? Okay, calcium, you should get calcium 2 plus. Coming over here, 1, 2, going back to argon. Bromine should be 1 minus. Lithium should be 1 plus. It goes backwards. Nitrogen will be 1, 2, 3 minus. We're gaining 3 electrons for nitrogen. Potassium, it's again another one of those positives. Potassium at 19 is closer to argon 18 than it is to krypton 36. So lose an electron. Potassium 1 plus. Carbon, this one's kind of tricky. Carbon's dead center here, 6. 1, 2, 3, 4 minus, or 1, 2, 3, 4 plus, helium. Carbon can be either 4 minus or 4 plus, and that's a big reason why carbon is so prevalent in life forms in our universe, is because it can make up a lot of different things, because it can be either a cation or an anion. It has a really neat dual nature that nothing else really has. So again, calcium 2 plus, bromine 1 minus, lithium 1 plus, nitrogen 3 minus, potassium 1 plus, carbon can be either 4 plus or 4 minus. And then you should know, looking at the charges here, and you can look back at this slide, which ones are anions, which ones are cations. Now the thing that I don't mention here in the slides is talking about some of these elements in the middle, like I do on the homework in like D block, and their electron configurations. So if I asked you, for example, Fe 2 minus, to map out the electron configuration of Fe2 minus, here's what you need to think about. I would originally go through and I'd write out the electron configuration for iron. So I would go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6, okay? Ending in 3d6. That's iron originally. Now I said iron 2 minus. Does that mean we add or subtract electrons? 2 minus, right, means that we have 2 additional negative charges. So we're adding 2 more electrons. So 1, 2, the electron configuration that you are actually writing is nitrogen's electron configuration. So you would just come back in, you do 3d8 and put, or sorry, nickel, ooh, not nitrogen, nickel's electron configuration. Okay, 1, 2, 3, 4, 5, 6, plus 2 more electrons, 7, 8, nickel. Okay, so if it helps you think about it like that, do the original element first and then either add or subtract electrons based on the positive or negative charges that you see on the homework. Okay, I hope that's helpful. I really, really appreciate you all sticking with the work. I've been loving the questions that I have so far. Please keep emailing me, letting me know if you need anything. I really appreciate the feedback. And hope you're all doing well. Miss you lots. Stay working on chemistry. I'm trying to find you some fun stuff to work on at home. And hope everything's going well. Bye, everybody.